Assalamu alaikum. Welcome to the next class in this electrical machines, and I'm continuing here also in the basic concepts of the magnetic circuits. So in the last class we discussed about the saturation. Today we'll discuss about the hysteresis, which is the we can say uh, which is the extension of the saturation. So let us take the same circuit. The only thing is that in the previous case we have a DC and we increase the current slowly from to lower value to higher value, but in only one direction. Now we'll take the AC. Like we have current, it is varying like this. In first half it is positive, first increasing, then decreasing, and then in negative part it is increasing and decreasing. So we'll discuss point by point what will happen to this BH curve and how this and what this hysteresis means. So this I should be AC current, that is, it should be of this type. We'll start from zero and we'll assume that there is no residual magnetism before the experiment or before we are increasing the current. When I is equal to zero, it starts from here. We know that H will be equal to zero since H is proportional to this I. So it will form the same BH curve which we have described in the last class. So it will be linear first and then it saturates. Let us say this point we increase up to this point and it saturates, and this point corresponds to the maximum value of the current. So at this point, this is the value of the magnetic flux density. After that, you will see that now the current will decrease. This has to decrease, but due to the hysteresis properties, or we can say due to the property that its magnetic dipole moment does not de-align because of the reducing field, they will retain their magnetic or we can say they will retain their alignment of magnetic dipole moments. You will see that this curve will not follow this curve, because when this decreased, at this point H is this value and B is this value. Now H is decreased in this manner. It has to follow this ideally, but because of the non-alignment, we can say because of the alignment, it retains the alignment of the magnetic dipole moment. It follows this curve, and when this H is equal to 0 or I is equal to 0, when I is equal to 0 at point A, that is, it has retained some value of the flux density. You can see that flux density is known as OA, and that flux density is known as residual flux density. Even if there is no current in the exciting coil, some magnetic field is produced here in the core. You might have seen this when we magnetize an iron nail and we take the magnet away from iron nail and we touch that iron nail to another iron nail. You might have observed that the iron nail is capable of attracting another iron nail. That is actually, we can say, experimental use, or we can say experimental observation of the residual magnetic flux density. Now after one point A occurs, after this the current will reverse. When current reverses, H also reverses. So this is the negative value of the H, and when negative value of current is given to this, it will try to increase its B in the negative direction. Since it has positive B, it will try to reduce it, and it will be of this order. And that means the value of the current, or H, which is equal to OB, is required to make this residual flux density to equal to 0. This OB is known as coercivity. Its value will be equal to ampere turn per meter. It's definitely the value of H. So this OB corresponding to this value. This is actually OB, the value of the current, magnitude of the current that is required to produce. This should have been, this point should have been O. That is this O. So this OB should be the magnitude of the current which is required to make this residual flux to be equal to 0 in this code. And after that, it will start in the negative direction in the usual manner that it would have started from over here. It is a linear region, and then it will saturate. And this F corresponds to maximum value of the negative value of H. And after that, you can see this negative value will decrease, or we can, yes, the magnitude of the negative value will decrease. At point C, it will be 0. and because of the inheritance property of this magnetic core, you'll see some magnetic flux will be retained in the negative direction, and this OC is also known as residual flux density, but in the negative direction. So then that is point at point C. When it is again increased from this point C to D, this much of H is required to make this flux density equal to 0. This again, this OD is also known as core residue in the negative direction. And then when it starts from here C to E, it then follows this path. It is from O to from D to E. When other cycle then occurs, this point is E, when other cycle occurs, it then traverses this path again and again. And in one cycle, it starts from here because we are assuming that there is no residual flux density. But since there is some residual flux, we can assume that there is no residual flux density, and in one cycle it has gained this path, then it will continuously follow this path from here to here in the other cycles. So the attains the retaining of the magnetic flux density, in other words, is known as hysteresis. And the loop that it makes in this way, you can see it's a loop, closed loop, it is known as hysteresis loop. So hysteresis is the dependency of the state of system on its history. Actually, it remembers this value from the history, because this value is actually part of the history, because at that point it is 0, but H is 0. It is, we can say, it is remembering the previous value of this H. We can say it is a memory. It is a phenomenon in which the value of physical property lags behind change in the effect causing it. This is the physical property, this B, it lags to the change of the actual property, actual quantity which affects this. So which causes this to change, but usually it lags. It lags means it has some memory. So magnetic induction, this phi or B, lags behind a magnetic force H. So that is what hysteresis means. Residual flux density or remanence or retentivity in this curve is known as OA or OC. Hysteresis loop is EABFCDE. It is EABFCDE. It is the hysteresis loop. Hysteresis loop will be there when there is saturation and residual flux. So these two are important to make this residual loop. For example, if we have other material whose pH curve is to be drawn in positive and negative direction, but there is no saturation and there is no residual magnetic field, you will see it will follow this curve, straight line in the positive quadrant, straight line in the negative quadrant. There will be no hysteresis loop, there will be no saturation. So there will be no hysteresis loop whose magnetizing curve is linear and who have no residual flux. Hysteresis loop is there for the magnetic material when mu r is very high. There will be no hysteresis loop for a non-magnetic material. For that case, mu r will be equal to 1 because there will be no saturation and there will be no residual flux. So their BH curve, or we can say, will be like this in the negative direction. Positive direction, I have shown you already, having slightly lesser slope as compared to this, but it will look like this in the negative direction as well. There will be no loop, hysteresis loop, for these type of non-magnetic materials. So you have to be very careful about this. Now, hysteresis loss. So what does this mean? What is actually hysteresis loss? So the area under this hysteresis loop will represent the energy density that is required to make it, and this type of energy density is usually dissipated as a heat in this magnetic material. So the more the loop area, the more will be the energy lost in the magnetic material. Actually, we can say this is the energy that is usually required to magnetize the magnetic material. So the area under the hysteresis loop will give us the energy loss per unit volume, that is the energy density, in one cycle of the current change. So when current changes or H changes in one cycle, there will be one hysteresis loop and it will result in the energy loss. The total energy loss in 1 second will be energy loss per unit volume in 1 cycle multiplied by the total cycles in 1 second. So the total cycles in 1 second will be actually the frequency. So energy loss per unit volume will be equal to in 1 cycle multiplied by frequency. This will be the total energy per unit volume. The total energy when volume is also known, it will be equal to energy per unit volume, that is the hysteresis energy, multiplied by frequency multiplied by volume. Let us say this total energy per unit volume per cycle is given by pH. When you multiply it by F and V, in that case you can calculate the total power loss of magnetic material in hysteresis loop. Usually this EH will be given as integral of H into dB or B into dH, depending on which term is the constant term. So since this is not linear, and this curve is not linear, this is non-linear. So if we integrate in this direction, we can keep this B constant. In that case, it will be equal to B dot dH. If we integrate it this direction like this, we can take H to be constant, and in that case, it will be equal to integral of B dot uh, H into dB. So that's why I have shown here both integrals. In order to avoid the need for computation of the loop area, which is very complex, Steinmetz gave an empirical formula for computation of pH based on the experimental studies, according to which this total hysteresis loss will be given as pH to be equal to Kh into F into Bm raised to power n. So this Kh is the characteristic constant of the core material. It depends on the core material. Bm is the maximum flux density, because in this case when I is the AC nature, it is increasing and decreasing, it will have a maximum value. H will also have a maximum value, and B will finally have a maximum value. So this B will also vary sinusoidally, it will have a maximum value, and that maximum value will be used in this formula. And n is the Steinmetz constant, which varies from 1.2 to 2.5, and often its value is taken to be equal to 1.6. So this formula is often to be used like this: Kh F, the frequency of the supply, multiplied Bm raised to power 1 by 1.6. So hysteresis losses dissipated as heat, that's why it is known as loss, because we are not actually getting some important work from it. Now some magnetic materials will come to see, as I already told you, you should also know this. We'll start from the paramagnetic material. These are the materials which are not strongly attracted by a magnet. They are definitely attracted by a magnet, but with small attractive force. For example, aluminum, which I had told you earlier, its value is mu r value, because this mu r will tell you whether the any element or any material is paramagnetic, diamagnetic, or ferromagnetic. So its value will be equal to 1.00. This is much of 0, which is perhaps 6 times 0.65. Air, it has 1.5 times 0.31, and platinum 1.0036. So what I mean to say is this: for a paramagnetic material, this mu r is slightly greater than 1. And in this case, the orientation of dipoles parallel to the applied magnetic field is not complete. In this case, it's not complete, and it requires a lot of magnetization to make it complete. So in that case, its magnetization is very small in the practical values of the current. So similarly, diamagnetic material which are repelled by the magnet, such as zinc, mercury, lead, sulfur, copper, silver, wood. I have particularly named those materials which are usually very useful in electrical engineering, especially aluminum. We have air, we have copper, we have silver. Silver is considered to be the best conductor, but it is not particularly used because of its cost. So usually will be using copper, aluminum, and air. So for this case, copper has a mu r value of 0.999995, and bismuth has 0.9983, wood has 0.99. Whatever be the case, it is 6 times 9 and 5. I have perhaps forgot the value of this silver. It will be definitely in the same range, and for a diamagnetic material, you will see that this mu r will be slightly less than 1. And for practical purpose, for both the cases, this mu r is taken to be equal to 1 when we use them. So they are slightly magnetized when placed in the strong magnetic field. They are also slightly magnetized. They are slightly magnetized. These are also slightly magnetized, but the direction of the magnetization is opposite. The magnetization act in the opposite directions to that of the applied magnetic field. That is why they try to this repel. They are repelled by the applied magnetic field. Again, their magnetization is not complete, and they need a strong magnetization to do that. And the practical value of the current, or we can say number of turns, is not so much. We can make it complete. The third is the ferromagnetic material which are strongly attracted by the magnet. So for them, UR ranges from several hundreds to many thousands. Usually, I have shown you earlier the value or range 1000 to 6 or 7000. They exhibit a strong magnetism in the same direction of the field. Whenever the magnetization is done, their dipole moments orient or align themselves in magnetic field so that they will form a strong magnetism. There are two types of ferromagnetic material. One is soft ferromagnetic material, and other is hard ferromagnetic material. The soft magnetic material has high value of μr. It has low corrosive force. That means we require less amount of current to decrease the residual magnetic field to zero. They are easily magnetizing and demagnetizing. That's why this low corrosive force is there. There is extremely small value of the hysteresis. When low corrosive force is there, there will be hysteresis loop will be very small. For example, iron and its alloys with nickel, cobalt, and aluminum. Hard magnetic material that will definitely opposite to this. Low value of μr, high corrosive force, that means high retentivity. That means it will be difficult to magnetize and demagnetize. They retain high percentage of magnetization. It's because when they retain the high percentage magnetization, their retentivity will be high, their residual flux will be high. They require more amount of current to decrease their magnetization to zero. There will be high hysteresis. The area of the loop will be very large. That means high hysteresis loss. And for example, cobalt steel and alloys of nickel, aluminum, and cobalt. The fourth one is the ferrites. They have the intermediate position between ferromagnetic material and non-magnetic materials. They have a square type of the hysteresis loop. For example, they are made of iron oxide, Fe2O3, with one or more divalent oxides of nickel oxide, manganese oxide, or zinc oxide. One important note is that hard magnetic materials, they are also known as permanent magnetic materials, or we can say permanent magnetic materials are nothing but hard magnetic materials, which are used for permanent magnetic DC motors. Those motors which have permanent magnet, we don't use their electromagnet, where we can get the magnetic field by producing a current. We can have a material whose there will be a good amount of residual magnetism, and it will retain there for a good amount of time. So we can call them as permanent magnets. So these types, hard material permanent magnets, are made from this alnicos, ceramics, or rare earth materials. So this way we can say the application, or we can see what are the different uses, where are they used uh, in case of when we use the hard magnetic material. So the hysteresis loop for the soft ferromagnetic material will be like this. You can say they have the high value of μr, that slope will be higher, retentivity or eminence will be smaller, their slope will be smaller, but retentivity will be higher. And retentivity will be higher, corrosive force will be higher. You will see there will be more area, there will be smaller area. And for ferrites, it will be of this type, square type of the BH curve, or we can say hysteresis loop. So I think I will stop over here. We will continue in the next class. Thank you.